So here we have some rows, some columns. So what type of a matrix is this? This is a square matrix. Square matrix means that if I have n number of rows, there is 3 rows here, then I have also n number of columns, there is 3 columns. Right, so this is a 3 cross 3 matrix. So this is the dimension of the matrix. This 3 cross 3 is the dimension. So this we have studied in math, right? But how are we going to apply this in CT? So basically, think of it this way. We have already studied about dictionaries. Yeah. Do you want to say something?
Ma'am, your voice is too low.
We can't hear it actually.
Absolutely.
Kindly just give me 2 minutes. I'll try to fix the audio.
Okay, now is the audio better?
Yes, ma'am. Now it's
Yes,
perfect.
ma'am. Clear.
Yes, ma'am.
Yes.
I was also not able to hear him. Okay.
Ma'am, is it the first session of week 9?
Yeah, this is the first session. Okay, so quickly I'll go through the theory part, not much. I mean, there are just 2 PDFs I want to discuss from week 9, and then we will go into the practice questions. Okay, so as we all know that in maths we have done matrix, right? Now in CT, this exact implementation we will be doing, except with the help of dictionaries. Okay, so all of you know what are dictionaries. We have these key value pairs where each key has to be unique, values can be duplicates. That's basically what is dictionary, right? And we can individually access any value we want using its key. So there is no need to traverse one by one. Okay, so second is we know what are nested dictionaries. So when you have a dictionary inside a dictionary, like your outer dictionary might look like this. It can have keys like A, B, C, right? And if each of these keys have, let's say, some values which are also in the format of dictionaries. So this is a nested dictionary then, right? This is exactly what we are going to use for implementing matrices. Okay, so I'll show you first how to do it step by step, and then we will see exactly how this applies to graphs. Okay, so graphs, any graph can be represented using an adjacency matrix. So adjacency matrix concept I'll discuss in more detail. That basically means that whenever, let's say if I have a graph with 5 nodes or n number of nodes, and there is an edge from node A to B, right? So in that case, in the matrix, we will have rows and columns where each row indicates one node and each column also indicates one node. So if I have, let's say, 5 nodes in my graph, there will be 5 rows in my matrix and 5 columns in my matrix. Okay, something like this. So let's take a smaller one. Let's take a 3 node graph. So A, B, C, 3 nodes I have. Let's say these are the edges. Okay, then if I draw the matrix, it will look like, so I should have A, B, C here as well and A, B, C here as well. So now A to A, is there an edge? There is no self edge, right? Or self loops. So from node A, there is no edge which leads you to node A. So in that case, we'll place 0. But from A to B, there is an edge. This is an undirected graph I have drawn. Okay, so there is no direction whether the edge goes from A to B or B to A. So in that case, A to B, since I have an edge between A and B, this entry will be 1. Similarly, B and A entry will also be 1, B to A, because this is undirected. Again, A to C, A and C have an edge joining them, so there will be 1. B to B, there are no self loops. B to C, there is no edge, so this is also 0. C and A, they have an edge in between, so this is 1. C to B, again, no edge, 0. C to A, C to C, again, no edge, 0. So see, these are the this is how you can actually represent a graph in the form of a matrix. So first we will understand how to use pseudocode to form these matrices, then we will see how to use graph algorithms using it. So in upcoming weeks, we will also study breadth first search. Okay. So BFS, DFS, these concepts are also going to be covered. Okay. So first, let's do a little recap of what are collections, what type of collections we have learned so far. We know what is a list. So list is a sequence of values. Random access is not possible. You have to traverse the entire list one by one. And for a value at position I, we have to start at the beginning and scan all the I-1 elements till we reach that value. So that's one characteristic of list. Again, it can be heterogeneous, it can be homogeneous. The elements can be anything in a list. Right? Duplicity is also allowed. Dictionary, we have key value pairs. This also supports random access, which is why this can be a better option for in lot of purposes instead of lists. Keys can be any arbitrary values, making sure that each key is unique. Now, next we will study what is a matrix. So, two-dimensional table. Two-dimensional table means we have rows and we have columns, right? So, it's a two-dimensional table only. We can have m number of rows and n number of columns. Okay. Now, matrix also allows you to do this random access, like a dictionary. So, if I have a matrix like this that I drew previously, something like this, okay. So, let me just name these. So I said I, J, K. These are the rows and same thing in the column also. So now if I want to access matrix IJ, can you tell me what is the value? So I represents the row. This is the convention. Okay, you can also flip it, but usually we will be always referring to the first index as the row index, second index as the column index. So for matrix IJ, what should be the value I should access here? First I
Two.
row. That means this is the row. Correct. Yes, 2. Once row is selected, next find the column index j. So this is the column. So this is the value. This is how you do random access using row and column index. Right. So by convention, rows and columns are numbered from 0. Okay, this I have just randomly taken. But when we actually do numbering, that is, we want to say let's say we have 3 rows. So the row numbers will be like index will be like 0, 1, 2. Okay. So if I have m rows and n columns, then this I value, or let's say from now onwards, we'll be using I as the indicator for row index. So if there are m rows, I value can range from 0 to m-1. And if there are n columns, similarly, j will be the column index. So that can also range from 0 to n-1. Up to this, is it clear for everyone? Any doubt?
Yes, ma'am.
Yes,
Yeah.
ma'am. It's clear.
Yes, ma'am.
Yes, ma'am.
So, yes.
Ma'am, I have one doubt about grading related. Could you clear it, ma'am?
Yeah, tell me.
Ma'am, what if like my quizzes were not going good? So what like I need to score like around 7.5 CGPA in term. So how much I need to score?
Um, you mean for to be eligible to write and term, or
Yeah, I'm eligible for right in term.
okay, so you want to maintain, you're asking what it will be for an A grade in CT.
Yes, you can say that. Like seven, I
So that's
want to make 7.5 CGPA. If I will not, then my parents will beat me.
okay. So just do one thing, you send me an email, okay? I will answer these doubts in the email.
Okay, sure, ma'am. Ma'am, can you share your email? I will text
Yeah,
you.
I'll give it in the chat. Okay.
Ma'am, chat is not visible. Wait,
You can find it in Discourse probably.
bro, I'm
Uh,
not able to access discourse, brother.
no, in qualified students do not have access to discourse. See in
No,
the
I'm
Gmeet.
not qualified, ma'am.
Okay, you're in foundation. All right, no
Yes.
issue. I will just share it to in this Meet chat. Okay, can you see that meeting chat?
Ma'am, I'm not able to access. Like it's a loading. It is showing.
Okay, then I'm just writing it here. I'll copy it from here.
Yeah,
Okay.
yeah, ma'am. Right there, I just take a screenshot. Mandepa@.
Here you can
Okay.
mail.
Yeah, thank you, ma'am. I mail you from my student ID, na?
Yes, yes, please.
Okay, thank you very much, ma'am. Very much.
Thanks. Okay.
Ma'am,
So,
I have a doubt.
yeah.
Ma'am, in the like you told in the graph is the direction matters, like A to B is same as B to A.
Yeah, so that is same for an undirected graph. Okay. In a directed graph, you'll have an arrowhead. Like if I have nodes A and B in a directed graph, if I want to draw an edge, I have to specify whether the edge goes from A to B or B to A. These are two different things. But in case of an undirected graph, you can give one simple edge between two nodes.
Okay, ma'am, and it's also like the matrix also the directional graph is also changed like.
Yeah, it will definitely change. So if I draw the same matrix for a directed graph, then if there is an edge from A to B, then only this A to B entry is going to be 1 in the matrix. The B to A entry will remain 0. Okay, I'll take
Okay,
all
ma'am.
these examples, don't worry. Okay, so important thing in dictionaries is that they support random access, and this is what we'll be using in this matrix approach also. See, so how to create a nested dictionary, we all know, right? That outer dictionary will correspond, so outer dictionary will have some keys, and against each key there will be another nested dictionary. That's what we have seen so far. Now, how to use this concept to implement a matrix, right? So here the convention we will follow is the outer dictionary keys will be corresponding to the rows. Okay, so for example, again, let's take that IJK. Okay, these are, let's say, the rows. Or if you want, I can take 0, 1, 2. Let's say these are the 3 nodes. Fine. So for 0, I will have an entry. Against that, you again have this. For 1, you will have an entry, and for 2, you'll have an entry. So these are the rows. Okay, so when I say matrix 0, means you will come to this. That means 0th row. Now in 0th row, what are the columns? You can store the same columns here. So 0, 1, 2, right? These are the columns. Of course, against them you will store some value. I'm not writing it. Some Boolean value, anything, whatever is required. And same will be there for all of these, right? So now once you have identified which row you want, then you go into the value part for that row. That is the nested dictionary. Now from here you will choose whatever column you want. So if I want the first column, I'll write this. So in the dictionary, actually, this will give me whatever is stored against this entry. So 0th row and first column. Okay, this is the convention we will be following. Outer key will always correspond to row, inner key will always correspond to column. So this is very important. Remember this. Now let's see the procedure. So this create matrix is the procedure name. Now we have to give that how many rows and how many columns we want. Usually we will be working with square matrices. So number of rows will be equal to number of columns. But there can be a case where you want, let's say, m number of rows and n number of columns, given that m not equals to n. So those type of matrices are also there in use, right? But mainly we'll be using square matrices. So you have to give those parameters here, that how many rows you want, how many columns you want. Let's say I want both 3, 3. So I'll give 3, 3 here. So first thing you do is create the dictionary, the outer dictionary, which is the matrix dictionary. So call it mat, it is equal to an empty dictionary. Now we will populate this. Now we take a variable, which is the loop variable, I, and set it to 0 initially. Now the while loop will run how many times? As many number of rows and columns that we want, right? So there are going to be one nested loop and one outer loop. So 2 loops in total we require to create a matrix, because for every row we need to create all the columns, right? Because this is the entry. For 0th row, you have to create all 3 columns. So once you get inside a row, then the control shifts to creating or populating all the columns for that particular row. So see the next line, while I is less than rows. So rows here is 3. I starting from 0. So how many times this will iterate? 3 times. 0, 1, 2. Okay. So let's say I starts with the value 0. So 0 less than 3, fine. What you'll do is create the entry for that. So let's start with the empty matrix. So right now I have created one key, which is 0. Against that, I have stored a dictionary. Right? This is what I've done so far in this line. Next, you need to have one more loop variable for your columns. So that is j. Again, j is set to 0 and it will go 3 times. Again, 0, 1 and 2. Now see, once I have created this outer key, okay. Now the control has shifted to this while loop, that j is equal to 0, and while j is less than columns, we'll continue iterating, and then only we can go for the next iteration of the outer while. So what happens in the inner loop? See, j starts from 0. Currently, what is the I value? Also 0. So what is mat of ij? 0, 0.
Yes, ma'am. 0, 0.
Okay, 0, 0. Yes. Not able to erase this one second.
Stand on the shore and toss it. We need you, Alyssa. Don't get yourself in a lot by state now. Because let's be real, humans are the actual infestation. Yeah.
I'll just write it here. Okay. Not able to erase that. So 0. And we have created another entry 0. Now, what is stored against this nested 0 or the column entry for 0th row? The value 0. So key is also 0, value is also 0 for this column. Okay. Now you increment the value of j. So now j has become 1. Again, 1 is less than 3. So create the second entry, 1. Against that also we are storing 0 because we are just initializing the matrix. Okay, we can later on change these values and populate it however we want. This is just to create the structure. Next, again for 2 less than 3, create the third key and again assign value 0. So what have we created so far in the matrix? We have created the first row. 0, 1, 2. So now all these are populated 0, 0, 0. Okay. Now once this becomes 3, now obviously the while loop condition breaks and you come out and increment I. So I this whole time was 0, right? Because we are doing for 0th row. So now I has become 1. Again, repeat the same process. So now I is 1. 1 less than 3, yes. So again, matrix of I, you will introduce one more dictionary. So now it should look like 1. And again, you do the same process. So again, 0, 0, 1, 0, 2, 0. Right. Same again when this becomes 2. 2 against that. So this is the row. And again, the columns against it, 0, 0, 1, 0, 2, 0. This is the complete matrix. Right. Is this much clear for everyone?
Yes, ma'am.
Any doubt? Okay. So once this structure is created or the nested dictionary is created, then you just return that. Okay, so return matrix. This is the whole dictionary will be returned. So this is how you create a matrix. Yes. Do you have a question, Sohan?
Yeah, ma'am. This is of which week?
9. Week 9. Okay. Now implementing matrices. Okay. Same thing. See, the same code, nothing changed. They're just showing that how it is getting created. Okay. So now my matrix. This is the matrix I want to create. This is the name of the matrix. And I'm just calling this procedure. Okay, I already know what this procedure does. That means I can call this procedure with any dimension of row and column and it will create the particular matrix with all values initialized to 0. Okay, so in my matrix, I have called this procedure. See, this is not a square matrix anymore. It has 30 rows, 45 columns. So it will create such a matrix and return. Where will it be stored? In my matrix variable. So basically, my matrix is the name of the dictionary. Now, how to process matrices? So to process each value of a matrix, we have to know the row index as well as the column index, right? Now, as I told you, by convention, we will be taking I as the row index, J as the column index. Now, for each row I of my matrix, see, once you enter this for each block, right? Now, this for each block will continue how many times? If I say that my matrix has, let's say, some 3 rows and 3 columns. So for every iteration of I, how many iterations of j will be there?
3.
For all the columns, ma'am.
3.
3. Yes, for all the
Three.
columns.
3.
So in total, how many iterations will be there of this entire for each block? 3
9.
cross 3.
9.
So that's what you do to access all the values, to process all the elements, right? So do something with my matrix Ij means once you have the particular row and column index you're looking for, you can do whatever operation you want with that element. This is how you access the particular element. See, from now on, instead of, I'll just show you once that you can also use this thing. If you want to take the column variable first, that is also fine. So you first access the column and then in that column, you can also access the rows one by one. But, for exam time, just do any one convention throughout, okay, so that you don't get confused by it. And try to use these variables like this, that I for row, j for column. This will just reduce the complexity or any kind of confusion. Otherwise, anything is okay. If you want to access column first, you want to access row first, same result. Okay. Now, iterating through the rows. So row indices are keys of the outer dictionary, we already saw. Column indices are keys of the inner dictionary. That is, for every row, there are column indices. Keys of D. If I do keys of a particular dictionary, it will produce what? List of keys in arbitrary order. So if let's say in this my matrix, this matrix that I've created, here if I write keys of D, what will I get? All the rows, but in arbitrary order in the form of a list, right? So let's say I want to sort this. So I'll just use the sort function. So sort keys of my matrix. So this will now give the keys in an ascending order by default. So that's what they have done. So for each R, that is row, this is the row variable. Instead of I am now using R. This is also fine. So for each R in sorted keys of my matrix. So first this brings out all the keys of my matrix in an arbitrary order in a list, and then the sort function sorts the list in ascending order. So if you have 3 rows and it came in the order 1, 2, 0, this will sort it into 0, 1, 2. Now for each of those rows also, you need to find all the columns again in sorted order. So where are the columns stored? In my matrix of 0, that is the inner dictionary. Now you find out the keys of that inner dictionary, those are your columns, and again sort them. So usually we do this sorting, why we will see in a bit, okay, in some questions I'll show you. So this sort function will by default do it in ascending order, okay. Now to improve readability, we are going to be using this rows and columns like this. So for each, whenever I say rows, this function will basically mean sort of keys of my matrix. And whenever I say columns, this will mean sort of keys of my matrix 0. So that we always keep it in mind that always the keys are in sorted order. So that we can go one by one, right? Because here arbitrary values can create a problem. So for each R in rows of my matrix, this represent sort keys my matrix. Okay, and this same for column. So now that we are representing by RNC, of course, you will also represent the element like that, my matrix of RC. This is the row index, column index. So you can also process this entire thing column wise, just you have to inverse it. So first you go for columns, then you go for rows, same thing. So this is how you can create and access elements in a matrix. In this particular slide, do you have any doubts so far? Anyone? Okay. So let's go to the next one. Once. Yeah.
We can also use in on non-sorted order, right? Why we use to
Yeah.
sort them?
I'll show you why we are using sorting. So in some particular problems, see, whenever I'm populating the dictionary, right? If I want to populate it row wise, okay. So I want to go row 0, column 0, row 0, column 1, row 0, column 2. But if I don't sort these in this order, then the values will not be populated in this order. right? Because by default, the keys function will return the keys in any arbitrary order. So if I take it in that arbitrary order, let's say I want to insert in, wait, let me share first. Yeah, is it visible?
Yes, ma'am.
Ma'am.
So see, let's say this is my matrix. Okay, so there are some, I'm just putting blanks and I'm trying to populate this matrix. Okay, so let's say I want to go in this order. First, I want to fill this space, then this space, then this space. Okay, because I have the values that I want to put here in this particular order. So now if I just use keys of matrix, okay, this can return in any order. So it can return something like this. Okay, and if I iterate through this, then in row 0, the first value will be populated in the last column. But I will not be aware of that, right? Because I don't know in which order the keys function has sorted or given this. This is any order. But we need a particular order in matrix when we want to populate with certain values. So we want to know that the exact order is in our hands. So that's why we are sorting. Once you sort this, then you know that definitely will populate this index first, then this index, then this index. That's why the sort. Okay. Now see, there is a very interesting example here. So we already have this thing in our course also, in BS degree also, there are these mentoring sessions, right? So for any subject, if you are, let's say, not doing very well in that subject, you require some extra help. So in that case, we assign a mentor to you, who is a peer only, okay, who is someone who has done that course. But how do we know that they are suitable to mentor you? It's that they have scored good in that course, right? So that's the criteria, that they already have a high grade in this course, so they can mentor other students. So that's exactly the criteria here. See, student A can mentor student B in a subject if A already has higher marks. But again, we don't want toppers to be mentors, right? We want that any person who has scored a decent good marks should be allowed to be a mentor. So whatever A has scored, okay, does not have to be the full marks, does not have to be a huge difference between marks. So we select this criteria that for A to mentor B in a specific subject, the marks difference should remain between 10 to 20 marks. That is, A has scored 10 to 20 marks more than B in this particular subject. Then A can be B's mentor. So this is the criteria. Difference between 10 and 20 marks. And A has the higher marks because A is mentoring B. Okay. See, create a dictionary for marks in subject. So how will I know? See, what is the goal of this problem is that we want to find out that who are the suitable students to become mentors and who are the suitable students that are the mentees, right? That are getting mentored. So how I can do this using matrix? First, I will create a dictionary where I will store the marks scored by every student in a particular subject. So let's say I want to work with mathematics first. So I will call this dictionary as math marks, and I will call this procedure called read marks, and I'll pass mathematics as the parameter. So what does read marks do? See, it takes any subject as parameter, in this case maths. First, it will create a dictionary. So this creates this marks dictionary. Okay. Now you have a while loop. So this while loop will just go through one by one all of the cards in the scores data set, let's say. And for every card, it will create this key value pair. That is, for every student, it is just recording the sequence number and against that the subject wise mark. So for maths, it will record the maths marks of all students. So each key value pair is sequence number is to maths marks. Okay. So once this dictionary is created, then it just returns the particular marks dictionary, which is now stored as maths marks. So math mark is looking something like this. Let's say 0 sequence number has scored 70, 1 sequence number has scored 80, and so on for all students. Okay. Now, see, now we want to create a mentoring graph for a subject. So mentoring graph means I want to know that who can mentor who. So I want to represent this in the form of a graph, which basically means representing it as a matrix. Every graph can be represented as a matrix. So for that matrix representation, what is my criteria? That if I see that M of ij is 1. That means there is an edge from I to j, right? And m of ij is 0 means there is no edge from I to j. So basically, if there is an edge from I to j, it means I can mentor j. And if there is no edge, that means I cannot mentor j. Similarly, if there is an edge from j to I, that means that j can mentor I in this particular subject. So this is the representation. Now, how to create this mentor graph? So for that, we have this procedure, create mentor graph. This is taking marks. Okay. See, this marks dictionary is what we saw in the previous one. This dictionary we created, right? So currently I'm calling it math marks. In general, it is called as marks. So whenever you want to do it for a specific subject, you change the name. Okay. So this particular dictionary has all the input for every student and what marks they have scored in a particular subject. So that dictionary you take as parameter. I am working with this data set now. Now, n is a variable in which I am storing length of keys of marks. So first of all, what is this length of keys of marks representing here?
Number of elements or number of
Which
keys.
is number of students. Right? That's the number of students is basically what this is, because every key is a sequence number. Now, mentor graph is a variable in which I'm calling the create matrix procedure we saw earlier, right? Now, let's say there are 30 students in my class. So n is 30. So how many rows and how many columns do I need to map every student to every student?
30 into 30.
30 into
30
30,
cross
ma'am.
30. Yes. So that should be the dimension. So in create matrix, I'm passing n comma n. This is my dimension. Okay. Now, once this matrix is created, one second. Yeah. Okay. So once this graph is created, now it is called mentor graph. So this will map basically who can mentor who. Now we need to go through each of the items in this graph, right? Each of the elements. And we know that since matrix is a two-dimensional structure, so we need to go through both rows and columns. So we'll need two loops. First loop is usually we are using the first loop for rows and the second loop for columns. So for each I in keys of marks, for each j in keys of marks. See, for rows and columns, both the values or the indices are basically same. If I have 3 rows, I have 3 columns. Here I have 30 students in the rows, 30 students in the columns as well, right? So 30 unique rows, 30 unique columns. So basically, number of iterations are going to be same, but for each I will have 30 iterations of j. So total 30 cross 30, this many iterations. So what is happening here? Now you pick one sequence number from keys of marks, which is I. Again, you pick another sequence number j, and you find out what is the difference between their marks, right? Whatever subject you're doing it for. So marks of I, we already have all this information in the marks dictionary. So that's why I took it as parameter. You do marks of I minus marks of j. Okay. See, it is good to do an absolute difference here. Why? Because of course I don't know whether who is suitable, if I should be mentoring j or j should be mentoring I. So the better optimized way is to do an absolute difference and then check whether that difference falls within 10 and 20. But this will also work. Why? Because see, here I can either mentor j or j can either mentor I. So I will check for both scenarios anyways. So for ij, I'll find the marks difference. Marks of I minus marks of j. Let's say I has scored some 80 marks and j has scored some 65 marks. So in that case, what is the difference coming out to be? 15. Now you check, does this difference lie between our criteria, 10 and 20 marks? Right. So basically, marks difference should be greater than equal to 10 and less than equal to 20. So this is satisfying both. So in mentor graph, in I to j, that is row I, column j, that entry should be 1. Here, if let's say I had scored 65 and j had scored 80, then what would happen? We get minus 15 here. So minus 15, then in this if statement, it will fail. It is not greater than equal to 10, less than equal to 20, which is correct. It is less than equal to 20, but this criteria will fail. And since it is AND statement, the whole thing fails. And the mentor graph ij remains 0. Okay, so whenever we are creating a matrix, all entries are initially marked 0. You only change those to 1 where there is a possibility of I mentoring j. And once this whole thing is done for every pair of student, then you return the mentor graph. So in the mentor graph now I can see whichever entries are 1, I'll take that corresponding row and I'll know that this row sequence number is suitable to mentor the column sequence number. That is, I can mentor j in this particular subject. This much is clear? Any doubt? Okay. Now see, I want to pair the students in some study groups. Okay, I know how to find a mentor now. That is clear. So A can mentor student B in one subject. Let's say A can mentor B in maths. But in physics, I see that B can mentor A. This is possible, right? One person might be weaker in some subject, stronger in some other subject. So of course, there can be this thing. So in that case, what will happen? See, in some graph, there will be an edge from A to B in the maths graph. And in the physics graph, there might be an edge from B to A. Right. So I know that these two people can study together. So I want to put them in a group. Okay. So study groups in maths and physics. So first, if I want to find such a study group, okay, then first I have to find out what are the mentoring graphs for each of the subjects. That is, who can mentor who in maths and physics separately. So just do that. Maths marks and physics marks. First, you create the dictionaries, right? So what does maths marks store? Each entry is the sequence number is to marks code in that subject. And for physics marks, each entry is the sequence number is to marks code in physics. Once you have these two dictionaries ready, now you can pass them as parameter in the create mentor graph that we saw earlier in the slide. And it will create a mentor graph for both of the subjects. So for maths, we're calling it math mentor graph, physics mentor graph. So now you have all graphs with you, that who can mentor who in physics and math. Okay. Next, how to find the suitable people in study group.
Hello.
Yeah.
Ma'am, can I explain this again? This pairing, pairing
See.
students in study group.
So let's say that A and B, okay, let me write their marks, maths and physics. Let's say A has scored 80 in maths, B has scored 65 in maths. Now A has scored 65 in physics, B has scored 80 in physics. So can I say A can mentor B in math and B can mentor A in physics? Is it possible?
Yes.
So I know these two people can study together. So I'll form a study group. Okay, that's what I'm trying to say, that this is just an example of how to create study groups and pair such students who are mentoring each other but in different subjects. Okay, so for that, first I need to find out what is this maths marks dictionary, what is the physics marks dictionary, which is nothing but mapping every individual student to their awarded marks in that particular subject. Once I have that maths marks and physics marks, I can pass them as the parameter for these two procedures, create mentor graph and create mentor graph here. One for math, one for physics. So math mentor graph is going to have which edges will be 1 in math mentor graph? If I can mentor j in math. So I to j, that will be a 1 entry, right? Row I, column j. So this matrix will be created here by this create mentor graph. Okay, this is the same procedure we saw, this one, create mentor graph. Okay, now once this is done, see, use the mentoring graphs to pair off students. So now I have to find out that who are the same students who are mentoring each other in different subjects. That means if A can mentor B in math, then the A to B edge or A row B column, that entry is 1 in maths. And in physics, if B can mentor A, then this row B and column A, this entry is 1 in physics graph. Is this correct?
Yes,
Are
ma'am.
you
Ma'am, can you repeat it?
Yeah, I'm saying that let's say A can mentor B in math, right? So in this math mentor graph, the row A and column B, this entry, math mentor graph, AB, this entry is 1. And physics mentor graph, if I'm saying that B can mentor A in physics, that case physics mentor graph, BA, this entry should be 1. Is this correct?
Yes, ma'am.
Yes, ma'am.
Okay. So we need to find out that who are these students who are there in both the graphs. That is the common ones. Okay. Common students who are having this mentoring relationship in both the graphs, in both the matrices. So they are obviously the pairs we are looking for, right? Study groups. So first you create a empty dictionary called paired. This empty dictionary, this what we will store in this we'll see. So for each I in rows of math mentor graph, for each j in columns of math mentor graph. Okay. Again, remember rows and columns of math mentor graph are in which order?
Good, ma'am.
A, B.
Ascending order, right?
Yes.
We told that rows and columns basically means sort of keys of math mentor graph, right? So these are keys are all sorted in ascending order. Now we will pick, let's say, row 0 or sequence number. Think of these as sequence numbers as they are student data. J is 1, let's say. Just for this one. Math mentor graph in the if statement. Now see. Math mentor graph ij is equal to 1. So if that is true, that means student 0 can mentor student 1 in math, right? So math 0 to 1, there is an edge. And physics mentor graph, I will check, can J mentor I in physics? That is there an edge from 1 to 0 in physics? If so, if both of these conditions are true, and we have to see that they are not already paired with someone else. Okay. So we are checking that how, and not is key paired I. So if I is already there, okay, if I is already there as an entry in the paired dictionary, that means I has already been paired off with someone else. So we have to make sure that both people are available to put them in a study group. Because see, one person can mentor multiple people, and multiple people can mentor one person in different subjects. So you have to keep all of these conditions in mind. First, we check whether I can mentor J in math. Then we check whether J can mentor I in physics. Then we check that whether I and J are already paired off with someone. That is, they already are present as keys in the paired dictionary. So if both of these, not is key paired of I, if both of these give true, not of is key gives true when?
If it is not paid to anyone.
Correct. That means if it is not a key in the paired dictionary, so not of false will give true. So if all these 4 conditions are correct, then we will say that, okay, I and J can be study partners and they have not been paired with anyone, so we can pair them in a study group. So paired of I, this entry you will create. So in paired dictionary, now you have 2 valid entries. One is I is to J and one is J is to I. Right? In different subjects, but of course we can keep them in the paired dictionary. That is, they can mentor each other.
Ma'am, I have a doubt, ma'am. Ma'am, in this key of dictionary, comma I, that is when we are doing that statement, what is the value that it will get? This key will return what in the dictionary of I and J. If we give this key of
See,
dictionary,
if you take this paired dictionary, okay, initially it is empty, right?
yes, ma'am.
So let's say first IJ pair, that is I took 0 and 1, let's say, some arbitrary pair, okay. So I at this point is 0.
Ma'am, your
J
voice
is
is low, ma'am. Cannot hear. Yes, ma'am.
0. Yeah, now can you hear?
Ah, yes, ma'am.
Okay. So I is 0,
Yes,
J
ma'am.
is 1. Okay.
Ah.
So I am trying to see that has I and J already been paired off with someone. So if they're already paired, that means they should already be present as keys inside the paired dictionary.
Ah,
J,
yes, ma'am.
right. So that's what this is key is checking. Okay. So when I say is key paired comma I, so this checks whether I is present as a key in paired dictionary. If it is not, then is key function will return false. Now see outside I have a not, so not of false will give true. So and true. Same thing I will do for J also, because both of these people should be available to be paired with each other. So I'm checking that none of them are already keys in the paired dictionary.
Ma'am, I'm asking like if a dictionary is created using I rows and J columns, and if you're checking is key of that dictionary, comma I, what value, I mean, it will
No, this
return
is
a
not
list
that
of,
dictionary. This is not a nested dictionary. Paired is a normal dictionary.
okay.
Okay. Paired is normal. Inside pair, it is like, see, in paired dictionary, Let's say sequence number 1 is paired with sequence number 2. Then 2 is also paired with 1. Then 3 is paired with 4. It's like this.
But in case of nested dictionary, what will be the case, ma'am?
Nested dictionary, if you ask like this, then it will check for the outer key. That is paired
That is
dictionary.
only the rows. Only
Yeah.
the rows it will check.
Yeah,
Isn't
it will
it,
check
ma'am?
only the rows.
But for if you want to check for the columns, then we have to go inside.
Then you
For
have to
each
give
row, we
that.
have to check.
Yeah, then it will be
Ah.
like paired of I and then comma
And
J. Then you check its
okay,
key.
ma'am. Thank you, ma'am. Thank you.
Okay. So study groups, how we are creating is clear for everyone.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. So paired is a normal dictionary. Okay. This math mentor and physics mentor graphs are the actual nested ones. Okay. Now see another example, popular students. Okay. So a student who can be mentored by many people is called popular. So let's say I am someone, I don't do well in any subject, so I need mentors in every subject. So in that case, I will be very known person because I have people from every subject mentoring me. So I'll be popular. Okay, that's the criteria. Now, create mentoring graphs for all 3 subjects. So I need to find out that who are these popular students, right? I want to find out who are the popular students. So can I just say that if I create mentoring graphs for all subjects, maths, physics, chemistry, people who are present in all 3 can be considered as popular people?
Yes,
Can I
ma'am.
say that? Right. So previously I was checking amongst 2 dictionaries. Now I have 3 dictionaries to check. Okay. So first you get this read marks done for all of them. Maths, physics, chemistry. This is wrong. Just math marks. Okay. So each of these dictionaries are storing against sequence number what is the marks code in that particular subject for all students. Now once you have these 3, you can create the mentor graph or the matrices or the nested dictionaries. That is math, mentor graph, physics, and chemistry. So now each of these dictionaries store what? That one person can mentor who? It's like this particular procedure. This one, right? So in this procedure, we are taking as like who is I? I is the mentor, right? And J will be what? All the J values that are stored against I is what? The mentees. That who are the people I can mentor. So this is a nested dictionary. Just remember this distinction that the read marks procedure gives rise to a normal dictionary and create mentor graph is the nested dictionary, which is the matrix. So once all this is created, now we can find out who are the popular students. So you have to count the incoming mentoring edges for each student. Okay. Incoming. Why I'm saying incoming? That means this is definitely a directed graph situation. Because see, whenever I have this I to J in any particular subject, let's say in physics, if I have an edge like this, will I be able to tell that who is mentoring who?
No.
Instead,
No,
if I
ma'am.
write like this, now you can tell I can mentor J, right? So all of these are directed graphs we are talking about. Okay. So see, you have to count that for every person, how many such incoming edges are there? Like for J, this is an incoming edge. So J has 1 incoming edge. I has 0 incoming edges, right? So I will find out that which students have the most number of incoming edges. They are the popular students. See. Now popularity is a dictionary I have created. For each I in keys of maths marks, popularity of I is set to 0. Keys of maths marks, I'm just taking any dictionary. Okay, you can do the same thing with any dictionary, maths, physics, chemistry, because all student data is there in every one of them. So I've just taken the maths one. So for each I in keys of math marks means what is I? Sequence number of student. In popularity dictionary, I will create an entry for I. So let's say I started with sequence number 0. So in the popularity dictionary, now I have this 0 as a key. And what is the initial value stored against it? 0. I haven't checked for any incoming edges yet. Okay. Now for each J in keys of maths marks, now pick another student. Let's say J is 1. Okay. Once you have picked this, now you check the if condition. is in math mentor graph if there is an edge from J to I, that is row J and column I. Okay, row J and column I. If this entry is equal to 1, then I'm saying popularity should be increased by 1. What does this mean? That J
J
is
will be
being
1.
mentored by I. Right. J is mentored by I in maths subject. So that's why popularity is increased by 1. Again, same I will check for
But
physics.
how we can say J is mentored by I can be also mentored by J, right?
No, this is directed, no? This is directed graph we are working with. See, here in math mentor graph, when we created the math mentor graph, let's go to that procedure. This one, yeah. Here, what is the criteria I'm checking for each I and J?
Okay, we are doing
That's
I
the-
minus J. Okay, I understand.
Yeah, I minus J. So once this criteria, this score difference remains between 10 and 20, then only see in mentor graph, I am putting this entry as 1, I comma J. This entry as 1, right? I'm not putting J comma I as 1. That means that J can mentor I. Okay, so these two things, be careful about it. It's not the same. IJ and JI are different. Okay, so see, popularity will increase every time I find an incoming edge. Okay, that means there is an edge towards J. So if J is some student who is mentored by, let's say, some I in maths, and it is also mentored by some I in physics, and also mentored by some I in chemistry. So in that case, how many times popularity index will be incremented? 3 times. See, there are 3 if blocks: maths, physics, chemistry.
Ma'am, but we're
So
incrementing I, right?
we are incrementing the value that is stored against each I. That is, in popularity dictionary, we are trying to maintain that for every sequence number. We are maintaining something like a popularity score or index. Okay. So currently, what are the entries inside popularity dictionary seen? Whenever we pick one sequence number of a student, we immediately create an entry for I, right? So like I picked this sequence number 0. So 0, I created an entry, and what is the value stored? Initially 0, because I do not know that who is mentoring this particular person. So next, I am just checking that who are the people mentoring this. So if I find such a J who is mentoring I, in that case, this condition will be correct. Then I can say that yes, there is an incoming edge. Right. Yeah, I think they have written the convention. This is reversed. No, this should be IJ is equal to 1.
Yes, ma'am. That's what.
Yes, ma'am.
Wait, let me check.
This is ordered graph, so
Yeah.
J is mentoring I. Here is it is.
I think this is wrong. So JI should not be 1. It should be
And
IJ.
also
IJ should be
incrementing the value of
there.
I.
We are incrementing the value of I. Okay, so here actually they have done the whole thing different way. I think. Right. Incrementing for I. So we are checking that what are the incoming edges towards I. Okay.
They're just checking that how many students he is mentoring. I think so.
See, what is happening here is, so here in the outer loop, I am picking I, right? And for each I am checking for all the J's, right? And J to I entry can be 1 if there is an edge. That means if J is mentoring I, in that case, this should be 1, correct? This
Yes,
particular
ma'am.
entry, if I take this code as it is, it means that J is mentoring I.
Yes,
Okay,
ma'am.
so that's what they're doing actually. This is correct. See. What they're doing is they have reversed it. Since I am checking that who can be mentored, not the mentors, right? That means when I'm talking about the
Yes,
mentees.
ma'am. We are checking for popularity,
Yeah.
and
So
then
here
there
I
we
is
should.
the mentee. I is the mentee. Okay. That means J to I, there is a link means that J is mentoring I. So I am finding that how many such mentors are there for this I. That's what. See, mentored by many students means that there can be many people in maths, physics, and chemistry who can mentor I. In maths, there might be 10 people who have that criteria for mentoring that is satisfied, and they can all mentor I. Right? So for all of those J's, this has to be implemented. So here I is taken as the
But
mentee.
ma'am, we are increasing I, so I is mentees.
Yeah, I is the mentee. That's why we're increasing I. See, popular student is who is mentored by many people, not the mentor. This is popular student is the mentee we are talking about.
Yes.
That's why this is reversed. Okay, so if there is an extra J to I, that means J mentors I.
Ma'am, in
that's why
between your voice is having some problem. I think so.
I think there's a lot of weather issues today. Also, one second. Is this better?
Yes, ma'am.
Yes, ma'am.
Okay. So see why popularity of I is getting incremented, because we are trying to find how many such people mentor I. I is the mentee. This code is correct. Okay. J is the mentor. I is the mentee. It is just written in the reversed way because we are trying to find the opposite thing. We are not trying to find I to J. We are trying to find J to I. That means J is the mentor and it is mentoring I. So for each I am checking how many such mentors are possible in each subject. Is that clear?
So,
Yes,
ma'am, your
ma'am, clear.
Yes, ma'am.
diagram order should be reversed, right?
Yeah, exactly. No, I don't need to reverse it. You can just change this to I. The I and J can be changed. So this one you can take it as I. These are all J's. Okay, this is what they have done. Now it is clear? Popularity index.
Yes,
Yes,
ma'am.
ma'am.
Okay. So once you have this value, so now in the this wait. Once this dictionary popularity is populated for all students, right? So now for every student I know that what is the popularity index that is stored against this. So if for some person one, let's say there are 10 mentors, it should be like this. So this popularity dictionary is now done. Next, now avoid duplicates. They're saying that a student who can be mentored by many other students is popular. So we created mentoring graphs for all three subjects and we counted the incoming mentoring edges for each student to find out who are the most popular ones. Now they want us to avoid the duplicates, so explicitly keep track of mentors for each student and count them. Means what? See, mentors and popularity. Okay. It can happen that one student might be fitting the criteria to mentor another student in more than one subject. Yes or no? Let's say A and B, maths and physics scores I'm checking. Let's say A has scored 80 in maths, 90 in physics, B has scored 65 in maths, and let's say 75 in physics. So can I say that A can mentor B in both subjects?
Yes.
Yes, ma'am.
Yes,
Now
ma'am.
in the previous code,
Come
in
again.
this code, A has scored 80 and 90 in maths and physics. B has scored 65 and 75. So can I say A can mentor B in both subjects?
Yes, yes.
So now the question is that if I apply the particular algorithm I saw here, then for this particular A and B, okay, A is one person only mentoring B in two different subjects. But how many times is he getting counted? Twice. Once in the math mentor graph, once in the physics mentor graph. So popularity is being increased twice, but for the same person, right? These are not separate mentors. So I want to avoid this. I want that each mentor, no matter in how many subjects they are mentoring you, should be counted only once. Is the issue clear? Duplicates.
Yes, ma'am.
Yes, ma'am.
Duplicates.
Yes, ma'am.
Okay. Now how I can explicitly keep track of who are the actual like individual mentors? So mentors is a dictionary, popularity is a dictionary. Initially both are empty. Okay. Now what am I doing? For each J in columns of math mentor graph, in math mentor graph. So what are the columns and what are the rows? Same student sequence numbers. So each
Yeah.
J is basically a student sequence number, right? See, in math mentor graph, this one, where is that procedure? Yeah, this math mentor graph, if I call this procedure, what does each row and each column or each entry in the dictionary represent? Look at this code. Mentor graph of ij is 1. I is the row, j is the column, right? So whenever a row and column entry is 1, it means I is mentoring j, right? Now,
Yes, ma'am.
so each j is a student sequence number. Okay. For every such sequence number, we are going to create an entry in the mentors dictionary. Now it will look like this. So mentors, this is the dictionary. Let's say first j is 0. Okay. Against that, we are storing a dictionary. See, value is empty dictionary. Now again, second for loop. For each I in rows of math mentor graph. Again, I is nothing but sequence number. We are just dealing with student sequence numbers. What am I checking? If math mentor graph ij value is 1, which means I mentors j in math. In that case, mentors j of I will be true. So what does this mean? J of I will be true. See,
I'm not
j is
understanding.
in this case. Okay, let me take some example. Let's say j is sequence number 0. Let's say I is sequence number 1. Alright. Is this fine? J is 0, sequence number, that is student with sequence number 0, I is student with sequence number 1. Okay. Now for that student with sequence number 0, I have created an entry in the dictionary mentors here in this line. And what is the value I have stored? It is an empty dictionary, right? Now for each I in rows of math mentor graph, if math mentor graph has this entry as 1, just tell me this much. What does this condition represent to you?
I is mentor of J.
I is mentor of J. If this is true, then this is being populated like this. The mentors dictionary is being populated like this. So what is my current J? 0. J is currently 0, right? In my example.
Yes, ma'am.
Yes,
So
ma'am.
that is the outer key. This one. Against that, I have stored an empty dictionary. Inside that, I will have the I value. So what is I currently? 1.
Ma'am, once
What
can
is
you
the
repeat? In between, your voice is too low.
See, J is 0. Now, if I find such an I for which math mentor graph ij is 1, means I can mentor J in math, then mentors J of I is set to true. So mentors J of I means what? J is 0, so 0th row. Inside that, I. This is the column. This value is set to true. Is this correct?
Yes,
Yes,
ma'am.
ma'am.
Okay. Again, I'm checking. If physics mentor graph ij is 1, means I can also mentor J in physics. Then again, mentors J of I is true. But does that mean I do another entry or does this entry already exist?
Already exists.
So now see how we are avoiding the duplicates. So if one person J, in this case 0, is being mentored by another person I, in this case 1, in multiple subjects, we do not make multiple entries. For each mentor, we only make one entry. So here, for this mentor with sequence number 1, there is only one entry, even though this person might mentor 0 in more than one subject. Is it clear?
Yes, ma'am. Clear.
Yes, ma'am.
The same thing you will check for all 3 subjects. That is, for every particular student with, let's say, for every J who is a mentee, we will check every I who is a mentor, and we will check that in whatever subject this person is mentoring, J, entry should only become once. For if there, let's say J is mentored by I in more than one subject, since this is a dictionary, you cannot by default have duplicate values, right? One cannot be there twice inside a dictionary. So that's why using a dictionary is very useful in these contexts. So that's what we are doing now. Last, see, once all these conditions are checked, this inner for loop closes. Now popularity of J is what? See, this is the popularity dictionary. At this point, what will be popularity of J? Length of keys of mentors of J. Let's say for some other student with sequence number 2, I see that they are also capable of mentoring 0 in some subjects. So again, 2. Again, some other student with sequence number 3 is also capable of mentoring. So in total, let's say I found 3 mentors for this particular student, right? So find out who are the keys of mentors of J. If J is 0, tell me who are the keys. Mentors of J will give the value, this dictionary. What are the keys of mentors of J? If J is 0, 1, 2, 3, these are the keys.
Yes, ma'am.
So keys of mentors of J, I found out these 3 are the keys. If I find their length, I'll get that as 3, which is nothing but number of unique mentors of J throughout all 3 subjects.
Yes.
That's the popularity index value now. So popularity of J, in this case popularity of 0, is going to be 1, 2, 3. Right? So popularity dictionary is just a normal dictionary. It is not nested. So it is like 0 is to 3. So from here I can tell that this particular student is mentored by 3 unique people. Might be that one of them might mentor him in more than one subject. I don't care. But unique number of mentors is 3. Is this clear for everyone?
Yes,
Yes.
ma'am.
Yes,
Just
ma'am.
go through these codes one by one by yourself. Okay, this is since we are building up on previous codes. So I have to keep on scrolling back and forth. So you just do the code one by one. Okay, in this particular order when you try to understand this at home. Okay, now we'll do similar students. So 2 students are similar if they have similar marks in all subjects. Right. So let's see. Yes. 2 students are similar if they have similar marks in all subjects. Difference is within 10 marks. So dictionaries with marks in each subject. So we have maths marks, physics marks, chemistry marks. So what is the criteria for student A and student B to be considered as similar is if they have scored, let's say in maths, physics, chemistry. Let's say A has scored 90 in math, 80 in physics, 85 in chemistry. And B has scored 88 in math, 75 in physics, and 82 in chemistry. Can I say that they're similar students? Is the difference for every subject within 10 marks?
Yes, ma'am.
Yes, ma'am.
Yes,
We
ma'am.
can.
So A and B are similar. Now
Yes.
I have to find out who are these similar students. Okay, these are all just examples to make you understand how we use matrices. So maths marks, again I will create the same 3 dictionaries using read marks procedure. Each of these dictionaries contains what? Something like this.
Serial number and their marks.
Marks, something like this for every particular subject, maths, physics, and chemistry. These are done. Next, what you do? Create a similarity graph. So graph means another nested matrix. So the procedure name is create similarity graph. It takes marks 1, marks 2, and marks 3. These 3 dictionaries as its parameter. What are these 3 dictionaries in our case? Maths marks, physics marks, chemistry marks. Okay, this is a generalized procedure definition. You can tailor it according to your need. So now N is length of keys of marks 1. I have taken marks 1. That means you can take any dictionary, maths, physics, chemistry, because the student number is same across all of them, right? So N is basically nothing but number of students. Correct? Once we have this, now similarity graph. In this, I am creating this n cross n matrix and storing it. So tell me, initially in similarity graph or matrix, what are the values stored initially?
0, 0.
Whenever we create a matrix, initial all values are what?
Zeros.
Zeros. So currently similarity graph is an n cross n matrix with all 0 values. Okay. Now come to the for each blocks. Again, two-dimensional table, so we use two loops. So for each I in keys of marks 1, for each j in keys of marks 1, these are just to go through the students one by one, right? See, pick any student here. Pick any student I. Now for this particular I, we will go through all of the j's, that is all other students. And we will find out the difference in marks, right? But see, this time I'm taking the absolute difference. Why I'm taking absolute difference? Because if I get, any ij pair, and I find out that, like, if I do I minus j marks, then there is some positive value, there is some negative value coming. That means that doesn't mean that j minus I will not check, right? I just need to make sure that the difference, the absolute difference between their marks does not exceed 10, right? That's how I can say that they are similar. So to absorb those negative values, just to take the magnitude of the difference, we are using absolute value. So I have to do that for all three subjects. So see, I'll take their marks from maths marks, physics marks, chemistry marks. Here, marks 1, marks 2, marks 3. So all the absolute differences are calculated for all three subjects for this IJ combination. Let's say I is student with sequence number 0, J is student with sequence number 1. Once I have calculated these absolute differences, next I will check the criteria. If each of these difference is less than equal to 10, see, the first difference, second difference, third difference, if all three of these are less than equal to 10, then similarity graph IJ is equal to 1. So that means if all of their differences are within this 10 marks magnitude, then they can be called as similar students. So in the IJ, in the similarity graph, okay, in similarity graph, if IJ is set to 1, can I also say that I can set JI equals to 1 as well? I
Yes,
and J are
ma'am.
similar students, right? So their difference in marks is going to be same only. Whether I check for I, whether I check for J first, whether I check for I first, it is going to, the difference will not change. I am just taking the absolute difference, right? So here this is better to be described as an undirected graph, because if ij value is 1, then ji value should also be 1, because they are similar. This procedure is clear for everyone?
Ma'am, but
Yes, ma'am.
if we take I as the outer dictionary and J as an inner key,
Hmm.
then the J value will be incremented, right? If we take as a dictionary
No value
or
is
if we take as
incremented
matrix.
here. See, we are just assigning the value 1. Here the value 1 means that I and J are similar. Okay, here
Once can you
we
take
are
a
not,
matrix and explain?
yeah. So, similarity graph. Okay, let's take a 3 cross 3 matrix. I'm just saying, let's say there are 3 students only. So, 0, 1, 2, 0, 1, 2. Now, let's pick this student and this student. Okay, so row 0 and column 1. If I'm checking for these two, and I find that for these two students, the absolute difference in all 3 marks, maths, physics, and chemistry, fall within 10 marks. See, absolute difference means I will take the difference in their marks and remove the symbol. Just take the magnitude. If that magnitude is within 10, so this condition next I will check. Then I can directly say 0, 1 entry should be 1. That means in this case, it is representing that 0 and 1 are similar students. But by that same criteria, can I also say that 1 and 0 should also be 1? That's what I'm asking. Can I say this?
Yes, ma'am. They are symmetric, but a confusion is that uh, they will duplicate or not, ma'am.
No, there is no duplicacy here. Now, see, duplicacy comes when I am going for such a relationship which should not exist in the reverse way as well. Like if I can mentor J, J should not mentor I. right, in that same exact subject. But JK and Mentor are in different subject. Here the question is itself different. I am asking whether two students are similar to each other. So if 0 and 1 are similar, 1 and 0 are also similar because they're essentially the same people, right? So
Yes,
that's
ma'am.
why I think here both of these entries should be 1. Row 0, column 1, whatever relationship this is showing, row 1, column 0 is also showing the same relationship between the same two people. So if this is 1, this has to be 1 as well. Clear for all? Any doubt? Here they have not given this, but this is something we can add here.
Okay, ma'am. Thank you.
Okay, so the summary is what? That we can use graphs as a very meaningful way of representing relationships. In the next week, we will see more on graphs. And matrices, we understood that by convention, we will take the first index as row, second index as column. Now, every matrix will not be symmetric. If ij is 1, ji does not have to be mandatorily 1. So we saw both instances. Okay, and we know now how to iterate through a matrix to get all the information. So how do you do that? You take nested loops. So for one I, we can check through all of the j's like that. So both the, I think theory part is done almost. So should we do some practice questions? Just 4 or 5 we can solve.
Yes, ma'am.
Yes, ma'am.
Yes,
Excuse
ma'am.
me, ma'am.
Yeah.
In the above pseudocode, I wanted to know some
Which pseudocode?
previous one, previous page.
Okay. This.
The above, yes, ma'am. When we had entered in the for each I in the keys of max marks, this is just basically the sequence numbers, list of sequence numbers.
Yeah. Just sequence numbers. Instead of maths, you can take physics also, chem also.
So for each j will again start from the same value where is I
Yeah.
starting from, right?
Yes. So of course, for a particular student, I mean for I, if I value is 0, then j value will also start from 0, right? But you cannot compare a student with himself. So that will always give you 0 difference of marks. So that one iteration will not matter because that's a self comparison. Okay, you have to compare with the other 29 students if there are a total of 30. Okay.
Ma'am, we can also take marks too, right? For each
Yeah,
I.
any. All of these dictionaries have the same sequence numbers only. The keys are same for all three. Just the values differ. Okay. Can you see this PDF, week 9 practice?
Yes, ma'am.
Visible? Okay. Okay. See. First question is saying, consider the following graph generated from the scores table. Each node in this graph corresponds to a student from the table. Okay. So this is again on scores data set. Each node corresponds to a particular student, right? So there is an edge between two nodes if the difference in physics marks of the corresponding students is at most 5. So when can there be an edge from I to J? If their difference of physics marks does not exceed 5, that means less than equal to 5, right? At most.
Yes, ma'am.
The graph is represented by matrix A, sequence number is used to, so graph is represented by this particular matrix, sequence number is used to label the nodes in the graph. So basically each node is a sequence number. Now the following pseudocode, the following pseudocode computes the matrix A. Select the correct code fragment to complete it. So we have to find out what is this missing code. Okay, we know what is the goal. We need to find that in this graph only those two nodes will have an edge if their physics marks difference is at most 5. So first in marks, I am storing read physics marks. This procedure will do what? See, control shifts here. Definition of the procedure says, marks is an empty dictionary. While table 1 has more rows, read the first row. So go through all of the cards one by one in scores data set. And for each card, take the sequence number as key and physics marks as value. So this is basically that read marks procedure we saw in theory, right? So once you return this marks matrix, this is what sequence number is to physics marks for all students. That is returned back here. Now you have n, which is length of keys of marks, that is number of students. Okay. Now this is the middle part which is gone. So let's see the options. First option is saying that you create a matrix n cross n because n is number of students. So this is fine. Now, for each I in keys of marks, for each j in keys of marks, if difference between I and j. So remember, this marks is done for physics only, right? Here, read physics marks, right? So we are only taking the physics marks. So I am checking if their physics marks difference lies between -5 to +5. Greater than equal to -5, less than equal to +5. Then A of ij should be set to 1. Is this correct?
But we can't know who is mentor of student, right?
No, this is not about mentoring. I'm just trying to see if they're absent. The question it is asking that each node in this graph corresponds to a student. There should be an edge between two nodes if difference in physics marks is at most 5.
Yes, ma'am, it can be done.
No,
can
ma'am,
this be
it
true?
cannot.
Why not?
Because ma'am, if we take one student marks is 4 and another student marks is 5, then the difference must be 9, -9.
If we take one student, let's say I. Okay, I's marks is 4. And you're saying J's marks is 5, right? This you're saying?
Yes, ma'am.
So if I do 4 minus 5, I'll get -1. -1 is greater than equal to -5 and less than equal to +5. So it is a valid value, right? The difference has to be at
Yes, ma'am.
max 5. So is option A correct? Looks correct. Let's see.
Looks correct, ma'am.
Let's see the other ones. Okay. Now same, you again create a matrix n cross n. Again go through the same values. Just check this condition. This is where the trick will be. So here marks of I minus marks of j. Same thing except we have removed the
Equals to
equal
sign.
sign. Is this correct then?
No.
No, ma'am.
No. Right? Because if this person has scored 10, this person has scored 5, then the difference essentially comes up to 5, which is at most 5. But this is not considered here. Has to be strictly less. This is definitely wrong. Here, what is the issue? Is there an issue?
Again,
Looks
the
very
same
similar.
issue.
Yeah, and also we haven't created the matrix.
And it's not taking a great matrix.
So this is also wrong. This one, will this
There
be
is no
correct?
negative sign, negative -5.
Yeah. So why this is not correct is because if this person has scored, let's say 60 and this person has scored, let's say 64, in that case, the difference is of 4 marks essentially, right? But -4 will be the outcome. So here the range should be between -5 and +5, right? To account for both sides.
Yes, ma'am.
So option A is correct here.
Option
This
A,
is clear.
ma'am.
Any doubt?
Yes, ma'am.
Let's do another one. So this is comprehension based, okay? You have to study this entire thing and questions 4, 3 and 4 are all from this data. So mainly
Ma'am,
graph
now your
questions.
voice is too low. Once can you check it?
Okay, can you hear?
Yes, ma'am, now it's okay.
Okay. So here, this particular data you have to study and this will be used in all 3 questions and in end-term examination also. Mainly you will see that graph questions are having part questions like this, okay? There might be some standalone questions also, but this is a convention. We usually do this. So questions 2 to 4, let's study the data. Consider the following table containing scores of n students in a class. Assume that all scores are between 0 and 100. Okay, that's our range. The scores in the first and last row are shown as example. So like this is 0th student, this is nth student, and their scores are given. Right. So this is not some subject wise or anything. This is just a random table, okay, with some student sequence number and some particular score. But the range of values of student sequence number is that there are n students, so 0 to n minus 1, and the scores can only be between 0 and 100. Okay. The actual scores may be different. Okay. So this is just an example that is given to you to show you the table. So refer only to the table's header to answer all questions. Now, this information is stored in dictionary S with serial numbers as keys and the corresponding scores as values. So that means that this S dictionary is something like this. Let's say 0 has scored 50, 1 has scored 40, something like this. Correct? A
Yes, ma'am.
graph G is generated from this table in the following manner. So now a graph G is generated from this particular table that is given. Given a pair of students ij, there is an edge from I to j if and only if i's score is strictly greater than that of j. So in my graph, the criteria is that if I want to have a directed edge, obviously. So I and j are two nodes. I to j, there is an edge. If and only if i's score is strictly greater than that of j. This graph is represented by a matrix A. Okay. So if I represent a graph using a matrix, that means essentially what collection am I using? Dictionary. More specifically, nested dictionary. Now assume that, so A is a nested dictionary, right? Assume that dictionary S has already been computed, that we already have this dictionary given. Now study this pseudocode. Tell me what is N? Length of keys of S means N represents what? Number
Number
of
of students.
students, correct. A is a matrix which represents what? The graph. So the graph, obviously, since we have n students, it should be an n cross n matrix. So this is the
Yes.
nested dictionary or matrix representation of the graph. Now for each R in rows of A, for each C in columns of A, if score of, that is S, let's say this is a scores dictionary. So if scores of R is greater than scores of C, then A of RC should be 1. Is this correct? According to whatever is given in the statement, it is saying
Yes,
that
ma'am.
there will be an edge from I to J if I score is greater than that of J. So that's what we're doing. Instead of IJ, I've written R and C. If R score is greater than C, then there is an edge from R to C. Okay. Now just answer these questions. First question is saying, a row R of the matrix has 3 entries that are equal to 1. Okay, there is a particular row R of the matrix that has 3 entries that are equal to 1 and the rest are 0. Which of the following statements about R is true? So if in this A matrix, there is one row like this, 1, 0, 0, 0. Okay, there is one such row. What does this represent? For any row R, let's say R1, R2, R3, there are 3 rows. Or, I mean, it has to go on, obviously. Let's say there is some R4 also. And there are columns also, C1, C2, C3, C4, and it goes on. So if in this entire R row, this goes on, okay, as many students as are there. N students, so N rows, N columns. If only one value is 1 and all others are 0, what can we say about R? First option says that there are exactly 3 students who have scored more than R.
No, we can't say that.
I'm sorry, I have actually written it in the wrong way. 3 entries that are equal to 1. So it's like this, and the rest of them are 0. So from this, can I say that it means that R has scored greater than 3 other
No.
students?
No.
So what can I say from this particular row? Just looking at this row, it has 3 ones, 1, 1, 1. All the other entries are said to be 0. When is an entry considered 1? When marks of
R
R is
score
greater
more
than
than
marks
C.
of C. Yeah. So what can I say about this row from here? That R has scored more than at least 3 students or exactly 3 students,
Yes, ma'am.
3, ma'am.
right? So first option is saying there are exactly 3 students who have scored more than R. Is this correct?
No.
Ma'am.
Which option? Exactly 3 students who have scored less than R.
Yes, C, option
Yes,
C.
ma'am.
Okay. The two options are just to confuse. See, at least 3 students, not at least. We already know exactly 3 ones present in the row. It means exactly 3 students have scored less. This one is saying exactly 3 students who have scored less than or equal to. So this equal to condition is not there. We only draw an edge when it is strictly greater. Okay, see the other question. This, yeah, this one. If R and C are two students with unequal scores, which of the following statements is true? If ARC is 1, so let's just take some score. Okay, let's say R has scored 65, C has scored 45. If A of RC is 1, then A of CR is also 1. Is this correct?
No.
No, ma'am.
Given whatever I have taken as the example, which entry should be 1? A of RC. R has scored greater than C, right? In order for A of CR to be correct or to have the value as 1, that means C should have scored more. So this first option is wrong. Second option, if ARC is 1, then ACR is 0.
Yes, ma'am.
Yes, ma'am.
It has to be 0. If ARC is 0, then ACR is 1. This is also correct.
Yes, ma'am.
But is it? You said yes. That's why I
No, we
asked.
can't actually. According
We
to the
can't
code
see.
which is given.
Yeah, I do not know what is R value, what is C value. It might be. Oh, okay. No, here I can say. They have given unequal scores. Nice. For equal scores, we won't be able to say. If they didn't say anything about the scores, then we won't be able to say. But since they've already mentioned unequal scores. So from here, if I see A of RC is 0, that means I definitely know that R has scored less than C because they cannot have equal scores, right? So if R has scored less than C, then definitely C has scored greater than R.
But according to code, we can't forward, right?
Scored, right?
Yes, S of
So
R is greater than S of C, right?
yeah. So see, C is nothing but it is representing a student sequence number, right? So at some point, whatever this sequence number is, it will come as a row as well, right? Because ultimately, this list and this list have the same list of sequence numbers.
Okay, ma'am. Now I got it.
Okay. So if R hasn't scored greater than C, then definitely C has scored greater than R. So this is correct. Last option, if ARC is 1, then there is insufficient information to determine value of ACR. No. In this case, we can determine because of this one statement that is given, that they have unequal scores. If equal scores were allowed, then we wouldn't be able to say. This is clear for everyone?
Yes, ma'am.
Yes, ma'am.
Okay, let's
Hello,
do the
ma'am.
Yes,
other
ma'am.
part. Yeah,
Ma'am, can you repeat the question number 2? I didn't get that.
this one.
No, ma'am, the previous one.
This.
Yes.
Okay, so this is asking row R of the matrix has 3 entries that are equal to 1 and the rest are 0. So how many students are there? N students. So of course there will be N rows and N columns, right? So for any row R, let's take R1. I'm saying that 3 of the entries are 1. That means in 3 of the columns, the 1 value is present and all the other columns have the value 0. So what can I say about R and C? See, when is an entry 1? When R has scored strictly greater marks than C. So if there are 3 such 1 entries, that means there are exactly 3 such people from whom R has scored greater marks. So this option is correct. There are exactly 3 students who have scored less than student R. Right. Clear now?
Oh, yes, ma'am. Yes, ma'am.
Now do this part question. Which of the following statements about matrix A are true? This is also MSQ. There is at least one row that has only ones in it. So will there ever be a row that has only ones in it? See,
No.
every sequence number is also going to be compared with itself, right? In that case, will you ever get ones, all ones in a particular row? Look,
No, ma'am.
just a small example. If I take 4 students, 0, 1, 2, 3, 0, 1, 2, 3. If 0 has, let's say, scored greater than all other 3 students, these are all 1. But can 0 score greater than itself? No. This difference
No.
will always be 0, right? So this will remain 0. So there can be no row that has only 1 0. At least 1 0 will be there because of the self-comparison. So option A is wrong. Option B is saying there is at least one row that has only zeros in it. This will happen for whom? The person who has scored the lowest marks. So for them, all the columns will have 0 values, including the self column. It has not scored greater than anyone else. So all the other columns.
Ma'am, again your voice is low. Once can I check it?
Now also?
Yes, ma'am, now it's clear.
Okay. So see, for let's say this particular student has scored the lowest marks in class. Okay. So for that student, what will be all the values in its column? 0, 0, 0. So all zeros are
Exactly.
going to be there for at least one person who has the lowest marks.
Yes, ma'am.
So option B is right. Option C is saying there is at least one column that has only zeros in it. Is that possible? One column with only zeros. See, here we are doing row to column. Okay. A of RC. This value is 1 when R has scored greater than C. Right? For one individual column, if I pick this column, let's say, what does this value indicate? That 1 has scored less than 0. Right? So is there a person who has scored so tell me, what will it take for this value to be 0? If 0 had scored the lesser marks than 1, then this value would have remained 0, right? But take any other column, let's say take C2. Why is this value 0? Because 3 has scored lesser than 2. That's why this is 0. Right? So
Yes, ma'am.
if this entire column was to be 0 for 2, all the values, if they were to be 0, then what is the actual logic? What does this mean?
Highest marks.
Is it possible? First think about it. Is this entire column to be 0? Is this possible?
No, for
So this
himself it can't be, right?
exactly. But again, see that if okay, for 2 if I check, so for this to be 1, for any of the values to be 1, that means there must exist one person who has scored greater than this particular person in the column. Right? If there exists any other person who has scored greater than 2, then of course in the column for 2, there will be at least one value, which is 1. Is that correct?
Yes.
Right.
Yes, ma'am.
So a column can have only ones in it. See, it is talking about only ones. So can a column have only ones? Because when you compare something with itself, it will always have 0, right? Because it cannot be greater. So just like one row cannot have only ones, one column also cannot have only ones in it. Same logic for the self comparison. Last is saying there is at least one column that has only zeros in it. So which is that column? Or who
Who
is that
scored the
person
least?
that has only zeros in it? Column. Let's say column 2 has only zeros. What does this mean? That the sequence number 2 person has scored higher than everyone else in the class. See, this is C value, right? This is R values. So R has to be greater than C in order for the entry to be 1. If the entry
Yes.
is 0, means that C is greater than R. That means 2 has scored greater than all other person. Forget about the self-comparison, that value is equal to 0. For all the others, it is also 0. And that means this person has scored greater than all other students. So there will be at least one such column. Is this question clear for everyone?
Your voice is very low.
I'm not sure exactly what is the issue. Okay, let me just change this. Okay, now is this a bit better?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay. So this 3 questions from this particular data is clear for everyone?
Can you
Yes,
explain the
ma'am.
Any doubts here?
Yes, ma'am.
last part again? The option.
This option, right? Option D.
Yes, please.
Who is asking? Yeah, okay. So I'm saying that it is saying that one column has only zeros in it. Is it true that there will be at least one column which has only zeros in it? So when does a column have only zeros? When the sequence number, this particular column, let's say 2, this is for student with sequence number 2. If this student has scored greater than all other students, then when you do row minus column for this particular column, will there be any one values that you will get if this person has the highest marks?
No.
R
No,
minus
ma'am.
C will never be greater, will never be a positive value, right? So there can be all zeros. For which column it will be all zeros? For the person who has the highest marks. And similarly, for which row it will be all zeros? For the person who has the lowest marks. Okay. So that's half of it. I'm not going to solve the other half right now because you should also try once. Have you tried? Has anyone solved the rest? Let's see how
Yes,
many
ma'am.
are there. 5 to 8. This is just a very short one. Okay. 10 questions are there. Okay, let me do one more. The rest 5 you will do on your own. If you don't understand, please send me. I will request something. We are having some issue in the discussion forum. Okay, so the TAs are not able to access it. We're trying to work on that, but for the time being, whatever issues you have, please mail to any of the instructors. Okay, me or Praveen or Arshpreet, whoever you want, just send a mail with your queries for now. Okay, once it is fixed, you can again post on forum.
Okay, ma'am. Thank you.
Okay, so I'll just do this part question. Let's do the first one. So continuing with the previous question, assume that now that same question. Okay, assume that matrix A has been computed. There is some issue with my background. Sorry, I'm not able to write here. Okay, not sure what is the issue, but let's do the question anyways. So continuing with previous question, assume that matrix A has been computed. Study the following pseudocode. Okay. So N is what here? N is length of keys of S. What was S in the previous question? S was the scores dictionary, right? Against each sequence number, we stored the scores. Okay. So length of keys of S is what? Number of students again, right? That is stored in where? Which variable? N. If I'm not able to write, it's very difficult. Okay, I'll just say it. If you have any issue, you ask me in whichever line. Okay, because I'm just not able to annotate here. Don't know what is the issue I have to see. So number of students is stored in N. K is 0. Sum score. Okay, sum score is a variable where I'm storing S of K. So tell me what is S of K?
The score of that person.
Score
K.
of student with sequence number 0. Right? Since K
Yes.
is initialized to 0. Now, walk. walk is a variable which is set to true, and hops is a variable which is set to 0. Now, while walk, that means while walk is true, what we will do? First, you entered the loop and you set walk to false. Now, for each C in columns of A, what are the columns of A? The previous matrix, sequence numbers of students, right? So, while true, once you enter the loop, for every iteration, you set walk to false first. Now you go through this for loop one by one. That is for every sequence number of student. What we are checking, if A of KC is equal to 1. If this is true, then K is assigned the value C. So tell me, in which scenario A of KC will be equal to 1? When
That means
K
K
is
is greater than C.
correct. When K has greater score than C. If this is true, then K is assigned the value C. Now, sum score, this variable which was previously storing S of K, that
That
is
means
score
we
of
are
K.
minimizing it.
Yes. We'll see what this actually does. Okay. But every time you see that for some KC, A of KC is equal to 1, then you know that K has scored greater than C. So in K, I am now storing C. Okay. Now sum score, which was previously storing this value, see, SK value, right? This was nothing but, okay, I'm able to use it here. So SK value was initially the score of the first student or student with sequence number 0, right? Now since K has changed, so SK has to be changed also. So this updated SK is stored in sum score. Now walk. Walk is now set to true. And hops is incremented by 1 and then you do exit loop. What does exit loop statement do?
Exiting the
Exit
whole
loop
loop.
statement will exit the current for loop, right? And go for the next while loop iteration.
Yes,
That's
ma'am.
what this does. So when will I do exit loop? When I find that this condition is correct. Then you will do an exit loop. So when we go through all of the students one by one, see, once walk is set to false for an iteration. Once walk is set to false, it gets set to true only here, right? Once it gets set to true, then you do the exit loop and you again go for the next iteration. So walk is now again set to true. So you can do the next iteration. But if in some student's case, let's say walk is set to false and then for any C, you could not find this A of KC equals to 1. What does that mean? That there
C is the
exists no
top.
such C. Yes, tell me. What does this represent? That if for no C, I find that this gets correct for a particular K, then what can I say about this?
K is at the top position.
K is at top or K is at bottom position?
K is at bottom and C is at top. in B.
Yes, C is at. That means K is having some score. Okay. A of KC is equal to 1 will only happen if K has some greater score than C. If this never happens, if we never find an A of KC value that is equal to 1, that means K has scored less than every other person, right? So in that case, the walk remains false and you cannot go for the next iteration. So now, understanding this pseudocode, now you have to answer these 4 questions. So value of all variables mentioned in the following questions represent the state of these variables at the end of execution of above pseudocode. Okay. So the variables will all remain same. Like whatever you see here, their state of values will remain same. Next question is saying, which of the following statements about variable sum score is true, irrespective of the contents of the score table? So score table can have the rows, or can be the content. What statement about sum score is true? So sum score is what basically? See, sum score starts with the score of the 0th sequence number student or the first student. And then it only gets updated whenever this condition is true. That we find such a C value for which A of KC is 1. That means K has scored greater than this particular C. Right. Then we store the smaller value or the smaller mark scored in this sum score variable. See, K is set to C first and then S of K we are taking. So what can you say about sum score? it is equal to the score of student 0. Is it always equal to student 0 score? No. In the initialization part, it is equal to student 0 score. That's how we are initializing. S of k is some score. So this is not correct. Option B is saying it is equal to the score of student n minus 1. Can I say this also? Do I know for sure that the last student has scored less than the current k?
No.
I also can't say that. Right. See, k is only getting updated if we find a smaller value, right? Some person who has scored lesser than k. Third option is saying it is the minimum score in the table. So once I have found the minimum score, or the person who has the lowest score, after that will some score ever get again updated?
No, ma'am.
No, right? Because see, once I have set k to that minimum scoring person sequence number, there will be no a of kc which is equal to 1, because no one has scored less than the person who has the lowest marks, right?
Yes,
So
ma'am.
which statement is correct here? C.
Option C.
D is what? It is the maximum score. So for maximum score, again, what will happen? It will never be stored in some score at the end of execution because it will get updated. We are finding the smaller one. The smaller score updates some score. So C is correct. Let's do one more. This one. Value of hops is equal to 0. Which of the following statements are true? What is hops here? See. Hops gets incremented every time you find a smaller score. If hops remains 0, then what does it mean?
K is at the least.
That means the
The
this
first number
0th
is at the
sequence
least.
number. This is the least one, correct. So student K has scored the minimum marks. The value of K is equal to 0 because that's how we initialized K. So both of these statements are correct. Okay, do this also. Question 7. Variable hops satisfies which of the following inequalities? So we have to see that what are the range of values that hops can take. It can stay 0. At max, what value can it take?
N minus 1.
At max, n minus 1. Why n minus 1? When will hops become n minus 1?
It can't take itself, right? K can't take itself. K.
Yes. So when will hops become n minus 1? When?
Last position.
The comparison
When
will
it goes to the
definitely
last
happen.
person.
A with A comparison will happen, right? Because see here in the code, while walk is true, right? For each C in columns of A will contain all the sequence numbers. So of course self comparison will happen. But hops will only get incremented when we find a smaller value. So assuming that we start with the highest possible value and the entire table is, let's say, sorted in descending order. How many times does hops get incremented? Every single time?
Yes.
So at max, you can have what is the value of hops? N minus 1. You can either have 0, you can have n minus 1, you can have any value in between. But you cannot have n because we started the indexing starting from 0. So basically 0 to n minus 1 is same as 1 to n, but since we are working with 0 as the first row as given in the data, so we will take this range.
And K is not greater than K, right? Can we take that situation?
K, here you are asking that if A of K and C is also K, right?
Yes.
So that will
okay.
never happen. A score cannot be greater than itself. Okay, so these, I think the next questions are, okay, it is, yeah, part of the same thing. So sum is set to 0. For each C in columns of A, sum is sum plus A of KC. Okay, so which of the following statements are true about sum? So basically sum is going to store what here? A of KC will be 1 when K has scored greater than C, right?
Yes,
When A
ma'am.
has scored when K has scored greater than C. So if we start with this, What can we say about sum? Sum is equal to 0. This is a bit ambiguous. I mean, is it continuing from whatever we did here? Where should this pseudocode be placed? That I'm not sure. See in columns of k, so we'll go through all of them. But here k is not initialized or anything. That means I'm taking the k value same as what was given in the original one, right? So they're saying sum is equal to 0. Why should sum be 0? If we go through the columns one by one, k value is not changing. Okay, got it. So if we start with the initial value of k, which is k equals to 0, if we keep that only, right? Then you run this for each block. So every time sum gets incremented when a of kc is 1. If k is 0, and it, let's say, I think for this to be 0, in that case, then k has to be the one with the lowest marks, right?
Yes.
But that is nowhere mentioned. This is a bit confusing. So even if I say is, sum is the out degree of node k in graph.
What is meant by out degree and in degree? Can you explain?
In degree means incoming edges. Okay, so if I draw, I cannot draw properly, but if these are two nodes and there is an edge like this. So this is an in degree for this node. Okay, this one.
Is it directed, ma'am?
Yeah, this is directed. Out degree means edges that are going out from a node. So for this node, this is the out degree. For this node, this is the in degree. Okay, in degree and out degree only matter in case of directed graphs. This question is a bit ambiguous. Okay, I think there is some more information required. Okay, I will discuss this one more time. Let me see if this is complete or not. Now, last two questions you do on your own. I will not discuss these two. You try to do these two, and we will again discuss this in Friday session if you are not able to do. But in the meantime, complete this on your own and then submit the graded assignment by 19th. Okay, I hope you will be able to solve right now.
Yes, ma'am.
Yes, ma'am.
Okay, and whatever issues you're facing, just mail us. Any of us, all three of us, four of us, you can mail. If you don't have their mail IDs, you can mail me. I will give the mail IDs. Okay.
Ma'am,
Okay.
could you please explain question number 6 a little bit?
6, this one. So it
Yes,
is
ma'am.
saying that if value of hops is equal to 0, what can we say about hops? So when will this value of hops be equal to 0? See, hops start with 0, right? It only gets implemented at line 30. Line 30 will execute if the if statement is
Your
correct.
voice is low again.
Okay, hops will get incremented if line 9 if statement is correct, then only, right?
Okay, ma'am.
Otherwise, hops stays 0. So that means if I start with the lowest score, then it will never get incremented. Okay. So 2 more questions you solve on your own. This 8th question, let me get back to you if it is completed or not. And submit graded assignment by 19th. I'll also send an announcement once this discussion forum issue is fixed. All right. Thank you, everyone. Thanks for joining.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.